What is the strength of the electric field near a line of charge? We're going to do an example now of computing field strength near a continuous distribution of charge, meaning that this chunk of charge here is a line of charge. It goes from here to here and the charge is spread out evenly throughout, as opposed to all the charge being discretely placed at one point that has no definable dimensions. This one is going to have some clear dimension, and this is tricky because in this kind of situation, if you were interested in, say, the field over here, this little chunk of charge is going to push it this way, and this little chunk of charge is going to push it this way, and this little chunk of charge is going to push it this way. For this continuous distribution of charge. So here's our line, and now we've got some dimensions. So our line is going to have charge magnitude Q. It's going to have length L, and it's going to have, and we're going to be interested in the magnitude of the electric field up here, some distance A away from the line along its perpendicular bisector. We're going to take this simple symmetrical case, at least for the moment. And when we're trying to make this computation, we have a basic approach to follow. And the basic approach is this, right here. Our basic approach is, one, define the charge element dq. The second is define dq, and in this case, the magnitude of dq using geometry and charge density. Then we're going to find out what's the influence of that dq by defining dE, and then add it all up. So that's the basic idea. So let's describe. Let's just say what do we mean by a charge element dq? Well, in this case, it's pretty. There aren't a whole lot of different ways for us to divide up this line charge. And I think the simplest way is to take a very short segment of this line charge and say that's going to be our dq. How short a segment? Well, the length of this line charge will be some infinitesimal length. Since we're on the x-axis, let's call it dx. So this infinitesimal piece of charge, which is infinitesimally long, dx. So I'm going to say this is my dq. And we've defined the charge element dq, check. Now the next thing is to define dq, meaning to say what's the magnitude of dq. Define dq using geometry and charge density. So let's find out what's the magnitude of dq. Well, we can do that by saying, hey, I know the overall charge on this thing. The overall charge is q, and its length is L. So what's some little subset of that length? What's the charge on some little subset of that length? And so we can describe dq, the charge dq, in terms of the overall charge by saying that dq is equal to the charge density lambda times dx, where lambda is equal to q over L. So that means that dq is equal to q over L dx. Okay, so that means that we have now polished off step 2. Step 3, write an expression for the element of field dE. What do we mean by the field element? The field element means what's the contribution to the overall field that will be made by this little charge dq. How much field can we say is due? How much of the total field at this point P is going to be due to this? Well, we know what direction it's going to be, and then we know that is going to point off this way. And so this is going to be our field element dE. And the question is, what's the magnitude of dE? Well, we know what the magnitude of field is due to a point charge. And happily, that's the idea of having a charge element, at least in this case, is the charge element is so small that it's basically a point charge. We know that the field for a point charge, according to Coulomb's law, is kq over the square of the distance between them. So let's apply that to our charge element. How far is the charge element from the place where we're interested in the field? Let's take a look at this triangle here that's created by the created by the y-axis and the line charge. We've got a what we have here is a right triangle. In this right triangle, the base is x, and this height is that distance a, and the hypotenuse is the place we're interested in. It's r. R is equal to the square root of x squared plus a squared. Okay, so if the distance between the charge and the field is square root of x squared plus a squared, then the square of that is just x squared plus square of that is just x squared plus a squared. So down here we can say x squared plus a squared. So that's how much the our charge element is going to contribute to the field here. Excellent. So that's another task that we can check off. We've written an expression for the element, the field element dE, how much our charge element is going to contribute to the field. Okay, next step, and it says if necessary. In this case, it's definitely necessary. If necessary, use symmetry to define the effective field element. Let's talk about what that means, the effective field element. We can see that this field element points off obliquely to the left. We also know that if we were thinking about a different charge, like if we were thinking about like a little chunk of charge here, that the field would point off to the right. In fact, we know that for every single charge element that we have over here on the right, there is some other charge element symmetrically placed over here that's going to create a field that's pointing off to the right. And these two field elements, this dE and the other dE that we would create here, these two, the horizontal components are going to cancel out and the vertical components are going to add up. So what we really are interested in is just what's the vertical component of this dE. Well, once again, we have this simple, clean, right triangle looking thing. And dE effective is going to be just one leg of a triangle where dE is the hypotenuse. If we have some little theta in here, we can say that dE effective is going to be dE times the cosine of theta. So what's theta and what's the cosine of theta? Well, we know theta is in this triangle, this upper triangle. Theta, that's the same as the theta in the top of this triangle here, because those are vertical angles. And that's got to be the same as, that's the same as this theta in our green triangle. So if the top of the green triangle is theta, well, I'm not that actually interested in the value of theta. What I'm interested in is the cosine of theta. So I can say that the cosine of theta is the adjacent over the hypotenuse, otherwise known as A over R. And a moment ago, we already said what R was. We said that, you know, R is x squared, square root of x squared plus a squared. So that means that the cosine of theta is equal to A over the square root of x squared plus a squared. So that allows us to write what the value of dE effective is. We said that the dE effective is equal to dE cos theta, and that's going to be dE times A over the square root of x squared plus a squared. dE effective is equal to kq dx over L x squared plus a squared times a over the square root of x squared plus a squared. And that's going to be equal to k q a dx over L a squared, or excuse me, x squared plus a squared x squared plus a squared to the 3/2. Okay, it's not pretty. My calculations are getting messy, but I think we're getting somewhere. And in fact, we've just done, I think we're nearly at the end. We've used symmetry to define the effective field element dE effective. And now what we're supposed to do is integrate dE to find E. Well, this actually is, in this case, is pretty hard to do. It's not impossible, but it is definitely a pain. I'm going to just write out where we're headed here. We're going to say that E is going to be the integral of dE effective. And if we want to add up all the values, the possible values of dE effective, we would do that by saying the integral from x equals negative L over 2 to L over 2 of that big ugly thing we had up there. So that's going to be KQA dx over L times x squared plus a squared to the 3/2. This is a doable integral. It's a pain in the neck. If I recall correctly, this integral is going to require 2 separate u substitutions, and this is not a course in calculus. So we're not going to go through the integral right now. The really important thing, the physics is now done, right? In fact, we should just say physics is now done. We can be like, yes, we're done. That is our Efield if we can perform this integral. If you can either do the u substitutions or you can look up the integral. And if you look up the integral of a squared plus x squared to the negative 3/2, it's equal to x over a squared square root of x squared plus a squared. And again, we're not going to go through the details. But at this point, we could take this integral, and I hope you can see a couple of things here that most of the stuff out front, these guys are all constants, and so if this right here is your integral, you ought to be able to plug in limits of integration and get an answer. Again, what's really important is the physics, not the calculus. The calculus is often easier than this. Sometimes it's actually harder than this. But that's the idea. You want to walk through these steps right here. We just did the last one, or we looked up the integral. You want to walk through those basic steps to get to the field strength due to continuous distribution of charge.